everybody, welcome to MSDOSX lecture number 4. Hold on, I didn't start yet. Today we're going to talk about, we're going to wrap up memory management issues and start you right in on the lab, either finishing up the asteroids lab from last time or jumping into Memory Management 2 lab, where you're going to get even more practice with memory management and reference counting. It's hand-hold-ish, so I won't be going to, I'm going to try not to go into as great of depth of detail for this second part and let you guys do more hands-on stuff during the lab. So, and connect, we'll do that for now. So, remember we have, we've got properties and the synthesizers for those properties. Remember, the properties take a, each property has got a mode or set of modes, such as copy or assign or retain. So now we kind of pushed aside the retain and the copy property modes until this lecture, because that's what they apply to. They apply to memory management, and they make more sense in this context. So the setters for a property, this is using the dot notation equals. The setter mode is the specify. This is how you specify how the setter works. If it is just a raw copy of a pointer value, if it is make a copy of the object, like you're calling object copy and assigning that pointer, or if you are going to assign the value of the pointer and retain it. So this is the default, assign. This just means set this pointer value equal to this pointer value. It doesn't mean anything else. It doesn't mean lock it down and retain it. It doesn't mean make a copy of it. It's just alias this pointer with this value. That's the default. Then there's the retain mode and the retain semantics, which means when you make this a reference, this pointer is going to be assigned as well. Don't make a copy of it. Alias the same pointer. But when you do that, also call retain on that object. So very, very helpful if you've got a couple of classes like window classes or window controller classes, and this is foreshadowing for the next couple of weeks. If you've got, say, a window classes that have aliases or pointers to or references to your views that are within your window, say you have multiple views or multiple windows that are referencing the same view. When one of those windows goes away, you don't want that view that's copied across a couple of windows, you don't want that going away until the last window is closed. So when you have references to that view, you can use the retain property for that reference, and and it works just like you manually calling retain before an assign. And you'll see more of these in context, which will make a little bit more sense. And I'll be talking more about this retain in a few slides. And then there's the copy, which is akin to calling copy on an instance. You get the pointer back that's a copy to that object, and then you assign that returned pointer. Under the hood, the code generation is exactly that. Retain just calls retain first and then assigns the pointer. Copy calls copy and then assigns the pointer. But this is a way that you can specify it at a higher level, at a semantic level, so that it's clearer for you in your code what is going on with your pointers and your references to your pointers. So here, and this is exactly what I was talking about. So we've got a property called property name. It's part of this object. It's the property. The mode for this property is assign, And when we do object.property_name, remember the dot operators are used for properties only. And when we do .property_name equals a value, this gets, under the hood, gets converted to object, this object, setPropertyName, which is a message that all objects have, and the new value. Does that make sense? Object.property equals value is converted under the hood to object setPropertyName with that value. Retain. Same idea, right? What I was just talking about. Object.property_name equals new value, and property name has the mode retain. Gets converted under the hood effectively to object setPropertyName to calling new value retain. Calls retain on this object, gets a reference to this object back again, sets it to the property name of this object. Copy, really straightforward too, follows the same rules. Object.property_name equals new value. So you'll notice that these the syntax looks the same across all three of these, right? It's what it converts to that is important. Object, setPropertyName, new value, copy. You get the copy of the value's object back. We set the property name to that new copy's pointer value.
And it's worth pointing out that you may be accessing properties using the dot syntax, but the compiler will actually generate a message call. It's not like it, under the hood, it does the same thing as message call. It actually generates a message call to replace the dot syntax access.
So retain and copy, as you can see, remember, we know retain, right? But copy, what is one of the side effects of copy? Not only allocating and creating a new and copying over the values of an object, but also increases the reference count. So copy and retain, the copy and retain properties increase the retain count. So when you use this property, you have to make sure you release it. If you replace a value that is already there, say you've got one object that you've assigned, that you've copied or retained using the property, then you assign a new object to it, it will call release on the original object that you retained. The last object that you retained via the property methods, either copy or retain, the last one that got retained, you need to make sure that you release. So it will release unique objects if they are reassigned, but it will retain them, and you will need to release them yourself. It does check to see if you assign an object that was originally assigned, it will check to see if it's a different one. It won't do a double release. It won't effectively do a double release or release before assignment, before retainment. It's smart enough to know it's the same object. Don't do anything to it.
Yeah, the actual methods that get generated for retain and copy are a bit more sophisticated than we implied, but there's a bit of cleverness. You have to make sure that you're not releasing an object that's already assigned. But don't worry about it. It's effectively when you say set object.property_name equals some new value, when that's got the retain mode, it calls retain on the object and then assigns the pointer.
Does that make sense? Okay, so this is what we just said. The last object does not get released automatically. You need to release that yourself, either with a release or an auto release. Then for the retain and copy properties, for properties that have the retain or copy mode, they need to be released when the containing object gets deallocated. So this falls into kind of the natural pattern, and we're going to talk more about this in coming weeks. But this kind of falls into the natural pattern of your parents need to make sure that you're cleaned up. You need to make sure that your children are cleaned up. You need to make sure that your children's children are cleaned up. So as you retain and release, you make sure that they're balanced. And as you get deallocated, you need to make sure that you call release on anything that you've retained so far. And they need to be balanced, one for one.
Does everybody understand why that last release is necessary? So we suppose we have a property that has the retain mode set on it, and then we say object.property equals object1, and so that will call retain on object1, right? Because that's what the retain mode does. And then let's say later on in our code we say object.property equals object2. The setter will automatically call release on object1, so that way object1 it's correctly handled the memory of object1, and then it will call retain on object2. And if you sign it a third time, it will release object2, call retain object3, and then you keep doing that. But what you can see is that the last one has a retain that hasn't been released yet. And so that last object that's been assigned needs to be released, and the common place to do that is to release it in dialog.
So when the container object actually gets deallocated, that's the point where you clean up and call release on any objects that you've increased their retain count through the property methods, either through the retain property mode or the copy property mode. And you'll see more examples of this, and you'll get to actually play with this in the lab too as well, making sure that you clean up everything and you do it in order.
But it becomes pretty automatic behavior. Anytime I declare a property that I set the retain or copy attribute, I just immediately go into dialog and put a release for it. And then at that point, I know it works. It's going to work exactly as I want.
And then if you have any additional retains, you can make sure that they're balanced with releases. But you know that at the outermost shell that you've got a retain that will happen when you set it, and you've got a release that will happen when the parent or the container is deallocated. So this is kind of a sidebar for the lab. This is what an empty class declaration looks like. I use this as a way to subclass off of NS object, so that you've got your own class that you can mess with and that you can override dealloc. This is what it looks like, just an empty interface and an empty implementation. It's like having an empty class in C++.
If you generate a new NS object subclass in Xcode 4, this is exactly what you get.
Right. It'll look I want you to understand kind of what the syntax looked like ahead of time, so that it wasn't really confusing when you got to it in the lab. All it is just an empty class definition, no instance methods, no instance variables, or class methods or class variables, other than what it inherits from NS object. So every NS object has got a retain count method or message. The objects normally an object will return its retain count when you call this message on it, or you call it with this message.
The built-in objects, however...
Yeah, the built-in objects and the framework objects will typically return you back like an unsigned long max, basically saying this is shared across applications, so this memory is being shared across applications, so never ever allow this to be deallocated, ever. So you'll see your objects and your subclassed objects will typically have their retain counts will be what you expect. If you call retain count on some of the the NS object class or any of the other direct classes, you'll probably get this huge number back out again. It means never let it be deallocated, even between application relaunches. So auto release complicates this idea of a retain count even further. So let's talk about that. First off, don't ever rely on retain counts for anything other than debugging. So you're gonna mess with them in the lab. You're gonna get used to it and comfortable with the syntax of it. You can use it for debugging, but you should never rely on retain counts ever, ever, ever. In production code, don't ever rely on retain counts. It's a really good way to shoot yourself in the foot.
They are highly, highly, highly unreliable.
Yeah, like you've seen, they're different for whether it's your classes or the foundation classes. There's also some really funky things that can start happening when you've got threaded objects and you've got things being deallocated or released or over-released and under-released. Don't rely on them. You can use them for debugging, but don't rely on them. Even when you're using them for debugging, take them with a grain of salt. They're not set in stone. There's a much better way to handle this, and we're going to talk about this in some future labs when we talk about debugging and using instruments. So there's better ways to see what's going on under the hood for memory management than using some of the raw debugging messages and methods. Take the time and be really cautious about and be really focused and persistent about understanding memory management. Understanding reference counting memory management is not only a great skill to have for Objective-C, but also in general for languages that use garbage collection. Understanding how this works leads to much greater insight to how a garbage collector works, how it works effectively, how it can cause you to trip and stumble, especially when you've got latency that gets thrown in, if you're doing stuff over the web and you're using web objects. It also becomes critical, it's crucial when you have an application that's running in real time, whether it's a game or you're running a simulation that's time-based. Having a whole bunch, allocating 100,000 objects and having them garbage collected all at one time is going to drastically affect the overall performance of your application and maybe destroy the user interface. It also, automatic reference counting wasn't available before iOS 5, I believe. So even if it was available on the Mac, it wasn't available on iOS devices. So you still had to do the memory management yourself.
Well, automatic reference counting, just to mention it, it's actually not something that works in the runtime. Automatic reference counting, the way it works is there's a tool that's been around for a number of years called the static analyzer that does static analysis of your code. And in particular, one thing that the static analyzer knows is it knows the rules for memory management, so it can detect when you've allocated something and you haven't released it properly. So automatic reference counting, all it does is it runs a static analyzer in your code, and everywhere it determines that a release is missing, it puts one. And everywhere it determines that a retain is missing, it puts one.
So this all happens at compile time. Right. It's all done at compile time, and
so it's only as good as the static analyzer.
Right. Xcode, so Xcode 4, and you can see the static analyzer kind of in work graphically if you do an analyze under Xcode 4. That's essentially the static analyzer working. So here's the horrific example of abusing retain count. Don't ever do this. You'll see old code, OS 10 and iOS code that used to do this. That check the retain count, and if it wasn't 0, just keep releasing until it reaches 0.
I know. It's a funny thing to look at, but why is this a bad idea? Can anybody say why? How is this breaking the rules? Why is this a bad idea?
Because if something else was using that had retained that object as well, you would be kind of calling release for it. And then
yeah,
wait,
exactly. You should only in any object should only call release as many times as it called alloc or retain.
So if you put it in a collection and then you did this, you'd release it out of the collection, and the collection, any access in the collection would crash. So avoiding cyclical references, there's a real art to this, and this starts becoming more and more apparent as you start building larger and larger applications, and especially as you start applying some of the design patterns that we'll be talking about later in the semester to your code. Essentially what that is your parent has a reference to the child, and the child has a reference back to the parent again. Can anybody see what difficulties or challenges that might represent? Think about the order of release and when dealloc is called. So if your child retains the parent and the parent retains the child, who lets go of who first?
What happens when you release the parent?
Yeah.
From external.
Yeah, child doesn't release the parent doesn't release the child, so you get caught in this. In this live lock situation where neither one of them can budge. So typically, the school of thought is, and the rule of thumb is, your child never retains your parent. You always retain on the way down. You never retain back up the chain. So your parent can retain references to your children, but your children never retain references to the parents or grandparent classes. The parent is the creator of the object and holds the child as an instance variable, which is really clear cut. There's this rules to avoid retaining cycles on this Coco with Love blog has a really good article about this and some of the pitfalls with this.
That's also a really good blog in general.
Yeah,
there's a lot of really good posts on that.
It's true. There's a lot. There's definitely some stuff that comes out of here from that blog. It's a good read. It's very educational. It's also not too thick and syntax heavy. It's good. So we touched a little bit on this last time, and I spoke kind of individually with people about some of the more specifics. So here's the graphical overview of auto-release pools, when and where they get released. So it's kind of hopefully clear up some of the fog, demystify some of the voodoo. So here is your main. Here is when you call NS application main, you essentially enter into this thing called the run loop. The run loop is basically sitting there waiting for events to happen, whether they're idle events or they're mouse events or they're timer events or they're magneto events, whatever events are generated. Remember, OS 10 and iOS, the iOS and OS 10 operating systems are all event driven and have been for a long, long time. And so it's basically you are responsive to events coming in, whether they're idle events or they're actual user events or other. So you enter into this run loop where you grab the event, you process it somehow, like you've pressed a button by pressing this portion of the screen, which is within these coordinates, which is a button that you've laid down in the interface builder. We talk more about this in detail when we talk about views and things later on. But as an event is generated, you process it, then the pool is drained. That's where it drains all of the objects that have been added to the auto release pool. Remember, it just calls release on those objects. If those objects have been retained somewhere else, typically the caller who originally called the prime example are factory methods where you've got like string with init with string, which returns you back an auto-released string. If you still need that, you call retain on it. When you're done processing an event and the pool drains, it calls release because it's been added to the auto-release pool, but you've still retained it. You've still set the count up by 1. You're responsible for it now, but now the NS string is not responsible. The factory method is not responsible for the memory management. It's done. It auto-released it. It said, "Cool, you hang on to it if you want it. Otherwise, it's going away when the run loop is finished." So this happens over and over and over again. It checks to see if your program is done. If it's not, it goes back to the top, gets an event, processes it, and this process can run through a whole bunch of layers of your code. This isn't like a separate thread. This is how I envisioned it when I first started using it. I thought of it as a separate thread that's running, and it's just constantly like throwing out objects at arbitrary times. That's why it seemed like such voodoo to me. That I had to make sure that I retained an object that I created, like it's really, really fast. I couldn't have a bunch of steps in between because the garbage collector monster the pool would drain and it would throw my object away and I would end up with a bum reference. It's not how it works. It goes through all of your code. It goes through all of the steps of your code as it processes one event, and comes back out, and it's not until it's come all the way back out when the stack is all the way cleaned up when it actually throws away an object. So you can call one of these factory methods, do a whole bunch of other stuff, and then call retain on it if you want, as long as you're not coming back out of your event loop, and you're not coming back out of processing an event and coming back in again. In between there is when those objects will get released. But if you're still within your same stack frame, that object will stay there until you've come all the way out. Does that make sense?
Yeah, as long as the reference is still on the call stack, it will be around.
And then once your app has ended, NS application main has finished, has terminated, then the pool gets released and you're all done. And your application quits and it closes. So allocation of the pool is here before the run loop. The pool constantly keeps getting drained in the run loop, in the meat of the run loop, and then the pool gets released once your application is finished and quits. So pools, as we mentioned last time, auto-release pools can be stacked. The latest pool that you've created is the pool that an auto-released object will go in. So you have the main pool that is created for you at the beginning. It's created for you for an iOS. The boilerplate code, if you look where the pool is created for OS 10. Did I get that backwards?
Both iOS and Mac OS auto-create the main pool. If you look in main.m, which is the entry source file for every project, it automatically creates a pool.
You can see where the pool gets created. If you will have to do this if you're doing multi-threaded programming, but every time you create a pool, every auto-release that's called until that pool goes away, until that pool gets deallocated, every auto-release call will throw the object into that pool, into the lastly allocated pool. Does that make sense? Stack of pools. Garbage collection, automatic garbage collection, yay! We don't have to do any work. We don't have to think about memory management, right? Well, no. So as I've mentioned many times before, performance is a huge hit with garbage collection. Not only is it a problem when you've got a lot of objects that are being released or that are being garbage collected at the same time, but it adds a little bit of overhead just with normal memory management. You don't get memory management for free. In C, you allocate a block and you use it, and then you throw it away, right? And when you start working in garbage collected environments, every increase, they're small, minuscule hits, but there's still an increase in the amount of time that it takes to increase and decrement reference counts, and when there's zero, call the deallocation. It's fast. It's still very fast, but there's still a little bit of overhead that's associated with it. The amount of objects that are left in memory gets larger and larger and larger when you've got a garbage collected memory management system. In C, you have very, very tight control over how much memory is allocated at any portion of time. In a garbage collected environment, you don't. So therefore, objects can end up chewing up a ton of your cache if they're not actually deallocated until later down the road. So if your garbage collecting environment says, okay, how much virtual memory do I have? That's the limit where I'm going to garbage collect, right? Worst case scenario, which means that your objects never go away. So they're always there. So your cache is always, the cache is always dirty. You're always in virtual memory, and it starts thrashing like crazy until the garbage collector actually runs and throws everything away, which, since it's virtual memory size, is going to take forever to go through to dump all of those objects. They've gotten a lot smarter with garbage collecting, so it's a lot faster. It works with the caches, a little bit more coherence there, but it's still going to create a larger working set of memory that's in use at that time, so the caches are not going to be quite as efficient. So you have to really consider how long an object actually stays around and lives, and when it gets garbage collected. You also have to make sure that you've got strong references to objects. When you allocate something in C, right, you put aside some memory, you put aside some more memory that's a pointer within a structure, it's going to stay there until you call free, right? It's not going away until you call free. However, with garbage collection, you have to make sure that you retain and you hang on to that object, and anybody else who aliases that pointer, you have to make sure that you have a strong reference to it. You have to call retain on it or copy, right? Otherwise, it's going to get it has the potential to get released out from underneath you, and you don't have control over that. So the don'ts for the retains and garbage collection and automatic reference counted code, they're in the lab actually. The lab for today, you'll see what Apple says about some of these things. Again, highly recommended that you follow the Apple guidelines.
Don't mix and match them. Just pick one. Either pick manual retain release, garbage collection, or automatic reference counting.
That's right. So you'll see in the memory management lab, you'll see that that at times you'll be using the retain release. At times you'll be using just the standard garbage collector. At times you can also turn our automatic garbage collection on if it's available to you. Then you can turn it on and watch it run and see how it works. It's pretty interesting to see, but don't mix and match. Don't if you're gonna be using some automatic reference counting and some of your own, retain and release pairings. You can do that because the static analyzer is just going to be adding some retains or releases where you've left them out. But it's much better. It's a much better idea to go wholly automatic reference counting or wholly your own control over the memory management with retains and releases. Questions? Cool. So continue with the asteroids lab and then start in on the memory management 2 lab. Memory management 2 lab has got there are bugs in there, and I'm hoping that at this point they are the intentional bugs that if you find that something's not working, keep reading on there. It may not be working on purpose. You'll also get very comfortable using the debugger with this lab as well. So if you have questions about the debugger and the debugger interface, especially if there's questions about the difference between Xcode 4 and 3 and 4, please let us know.
Okay, and I have sign-in sheets again. If you're still on the wait list, the way I'm going to do this is basically people that continue to show up and sign in on the attendance sheet that are on the wait list, I'll just add. Since we seem to have a small enough number that we are okay in the room, if you show up and you are on the wait list, I'll add you. So just remember to fill in this before you leave.
Boom!